Hi, this is a test lecture for computational microelectronics. So this is the lecture one. And okay, welcome. So to the computational microelectronics course, the code number is EC7114. So my name is Sung Min and I'm affiliated with the ECS. So in this course, you can find many resources. In this year, we have different repositories, a live repository. This is alive and this is archive. So you can find it in this uh, address. So github.com and my ID and CM Computational Microelectronics 2020 fall semester. So also you can find my lectures, recorded lectures in my YouTube channel, and it has now very simple address, or just type my name in your YouTube search tab. And evaluation. So evaluation here means that you have to attend every lecture. So this is a mandatory one, and that will be 20% of our overall score. And every week you will have homework problems, and that will take the half of your full score. And at the end of our semester, I will give you certain theme for your final presentation, and you have to prepare your own video for this course. So you have to make a presentation, then I will just watch it and give the score for this final presentation. So for students from the Department of Physics or Material Science and Engineering School, I wanted to announce that there is no advantage or disadvantage rule for students from those background. Let me just dive into our first one. So this is infinite potential well problem. Here we have a particle in an infinite potential well. Infinite potential well here means that our electrons are confined in a physical range from x equal to 0 to x equal to a. Within this area, then our electrons can move freely because there is no electric field inside it. However, when it hits the barrier, like here x equal to a or x equal to 0, then it feels that it is prohibited to overcome the potential barrier, so electrons cannot move into this barrier area. Our electrons are only existing for this area. Then this is corresponding to infinite potential well problem. The infinite means that the barrier height is infinite. Then natural question is there any problem like a finite potential well problem? Yes, of course, we have it. Actually, this infinite potential well problem is just a limiting case of a more practical finite potential well problem when the barrier height goes infinity. For example, between silicon and silicon dioxide, our representative semiconductor material, and our representative insulating material, between them we have about 3.9 electron volt differences in their conduction band levels. 3.9 electron volt is quite a large number for our usual electrons. For them, this number is too high to overcome. This structure, for example, let's say that we have a silicon and sandwiched by silicon dioxide layer and silicon dioxide layer. From the viewpoint of an electron inside this silicon, these two layers should be regarded as just a forbidden region where potential is too high. So in this case, we can find that this infinite potential well is really corresponding to this practical system. The natural question is, can you find this kind of system in the reality? Yes, of course. We have certain devices called MOSFET, and there we have silicon layer for charge transport and oxide layer controlling the property of electrons inside the silicon. Our well-known device called MOSFET is really corresponding to this structure, silicon sandwiched by silicon dioxide, and this structure can be easily modeled as infinite potential well problem. Okay, so now you understand our lecture is not only for just scientific interest, but this is really related to state-of-the-art devices. So then our goal is to understand the electronic structure inside this silicon area, because when we understand the electronic structure inside the silicon channel, then that is related to the transport characteristics of our electrons inside the channel, and that is eventually related to the terminal current of our MOSFET made of this simple infinite well structure. So obviously our ultimate goal is terminal current for a certain device. So in order to understand terminal current at a given terminal voltage, then we have to understand internal transport characteristics. So that's the reason why we start from this infinite potential well problem. Okay. Now, once we have this infinite potential well, then we know that we have to solve Schrödinger equation. Schrödinger equation simply say that the sum of kinetic energy and potential energy should give us certain eigenvalue. So for a given eigenvector psi, we have an eigenvalue or eigenenergy E, and it is just the eigenenergy of an operator called Hamiltonian. So Hamiltonian is simply means the sum of kinetic energy and potential energy, and that generates the total energy for this system. So total energy of our electron is given just number E, that is related to the oscillation frequency of our electron. However, in this case, since we assume there is no potential value inside the system, so V can be regarded as just 0. Then we have a simplified form like kinetic energy operator and operator and psi equal to E. So this is okay, this is operator on operator, and this is a scalar. So please have a look at. Then when we explicitly write it down in a differential form, then we can find this equation. Yes, very clear. after that, boundary condition from the infinite potential well approximation, then we have to say that wave function should vanish at x equal to 0 and x equal to a. So when we just move this leading coefficient to the right hand side, then we can simply find that, okay, this is just to say the second order derivative of our wave function should be a certain number. This is scalar number. Then yes, that's it. Then the problem now becomes, what is eigenvalue or eigenvector of the second order derivation operator. Okay, operator. So now our problems becomes or transformed to this simple question: what is eigenvalue and eigenvector of our second order derivative operator? When we have a second order derivative of a certain function, then it is just the same. However, this is certain negative number. Then in this case, we assume that psi will be something like sine or cosine, because when we make a second order derivative of a sine function, then it becomes just a minus sine, and cosine also we can find when you take a second order derivative, we can have minus cosine. Then therefore we have to say that these are two possible bases for our equation of cosine kx or sine kx can give us the wave function f of sine. However, in this case, if we say psi at x equal to 0 should vanish, then it simply means that when we enter just 0, then a1 and it should be 0. So since a1 equal to 0, then we can easily remove it here. Wow. Then only we have a2 times sine kx is the available form. And let's apply another equation or boundary condition. So x equal to a, wave function should vanish, and in this case a2 sine ka. Of course, in order to satisfy this boundary condition, one possibility would be a2 equal to 0. However, when we adopt this condition, then wave function just vanishes. There is no electrons. So this is not of our interest. So this is not. And the second possibility is happen to be sine ka equal to 0. Please note that a is a given size of our system. So this is a given number, or just a given number. Then our question is, what is the condition for k to satisfy this sine of ka vanishes? So of course, when we have k times a equal to integer multiples of pi, so a certain integer, then it can satisfy this relation. So sine of ka equal to 0. So therefore, our conclusion is k should be certain integer times pi divided by a. You know it quite well. And if we remember that k square is defined as this relation, then from this information we can easily recover that E, which is given by half k square 2m is given by half square 2m and k squared. So a squared, pi squared, and our integer, which is squared. Once again, our wave function, which is corresponding to a2 sine kx, when k satisfy this kind of quantization condition, when we have this kind of wave function, then there is corresponding eigenenergy here, which is given by certain number multiplied by squared integer. So wave function just follows this rule. This is corresponding to our k, and this is corresponding to our squared 2m k squared. Okay, so I think that is for the first lecture. That's easy, and you have learned it already in your general physics course, but we have made a simple reminder for this simple problem. Yes, that is simple, but this is widely and repeatedly used in our course. Therefore, I want to start from this simple reminder. Okay, so then let me just finish our first lecture with this homework announcement. So this is due date is September 7th, so next Tuesday. So we have only one problem, and simply log in into your GitHub site and please watch it and start in our lecture repository. And after that, make a pull request with the file including your student ID. So it's like how can I say, our CM2020 app, and please make a folder like S, for example, like this, and please make a file readme.md, and this readme.md should contain your student ID 2013 and your name like this. Okay, this is Korean. So please make a file like this, and you should make a pull request for this readme.md file. Oh, how can I do that? If you are a newcomer into the GitHub site, maybe you will be a little bit confused. So in order to help you, I just made an example folder like whose student ID is 2000 and 0000, and there please read its own readme.md file, and you can find the way how to perform the first homework. Okay, so in order to give you more concrete understanding, let me just visit here. Then here you can find the folder. Then when you read readme.md file, then it is summarizing how can you make a pull request. First, fork your fork the master repository. So since this is our all shared common one, therefore it is not possible for you to change it directly by forking this repository. Then you have your own repository. Then you can change it by yourself. You can add a new file. Then in your new file, you can add, for example, your repository name and s and your student ID and slash readme.md. If your student ID is 2000, then it should be this way. And write your student ID and name. So it should contain this one line. And by clicking commit changes, your file is saved in your local repository, not in the master repository. So like this. So therefore, after make this readme.md, you should make a pull request. That is our original repository, and as a user or as a student, you can make a copy of it by fork. Then you can add it here, certain addition. After that, you make a pull request. Then I will just accept your pull request, and once that is accepted, then your added portion is added to our master repository. There are many students, and all of them perform their own homework. Then they just make a fork, and usually they are the same. Each of them makes a pull request. Then what will happen? So the reason why we introduce this subfolder for each student is in order to separate their contributions. Then although you make your certain repository and you make your certain another repository, another subfolder, however, they do not overlap. When we make this pull request and another pull request, and when I accept all of them, we will have this kind of newly added information. However, there does not occur a conflict between these guys and these guys and these guys. This is the first homework. There is nothing related to our course. Just do a simple exercise for our GitHub, because your homework, later homeworks, should be submitted to this GitHub. Let me just finish this lecture. So today is just a short exercise and short announcement, and we will move to the main story from the second lecture. Thank you. Bye.